Okay, so we're going to get into some of the core material starting today. There's a whole language of nonlinear dynamics that we're going to use extensively throughout the class. This lecture is going to hopefully calibrate everybody on that. I would guess that there's some of that language that you haven't used yet. I mean, some of you will know a lot of it, but I thought I heard a joke in there. I think linear dynamics is sort of a thing. Nonlinear dynamics is a bit like saying non-elephants, right? I mean, it's kind of everything else. So it's a big potential topic. But I think there's a few core ideas that I really want to land because we're going to use them throughout the term that I can get across with some pretty pictures and some simple definitions. Okay, so that's our goal for today. I'm going to start off with the simple pendulum. We had a discussion on Piazza already a little bit about this here, but so first of all, when I say simple pendulum, it's not a universal truth, but most time when people say simple for their models, they're talking about point masses instead of inertial masses. So I'm going to go back and then, just like I did for the double pendulum before, I'm going to write a version of the pendulum that just has a mass at a point here. I don't have to worry about moments of inertia directly. Okay? Gravity pointing down, theta. The equations of motion are kind of a subset of what we did for the double pendulum, but they follow fairly simply. So if I write the kinetic energy, which we always use T for, it's just 1/2 mv squared. Turns out in the kinematics that is always 1/2, the v is L theta dot, so m/2 L theta dot squared. The kinetic, or the potential energy is going to be U is negative mgl cos theta. And that's really all you need, plus a few derivatives, to put that into our standard Lagrangian toolbox. But I want to make sure you understand where the torques and dissipations and other things come from too. So in the notes, I show you a few examples of deriving the Lagrangian, but you define the Lagrangian as the kinetic minus the potential. You do your derivation like this. Okay, since I've only got one angle theta here, it's just a scalar equation in this case. Okay, and if I take these derivatives, if I take the derivative of this, the equation that pops out is ml squared theta double dot plus mgl sine theta equals q. Now, so let's think for a second about what's q in this Lagrangian equation, right? The Lagrangian's talking about all of our conserved quantities, our kinetic and our minus our potential here. This is the generalized force. The Lagrangian's doing all of its work in the coordinate system defined by theta in this case. So we want to be able to think about what a force looks like in the coordinates of theta, the generalized force. In that case, here it's just going to be like a torque applied here. And we have a few different torques that are of interest. I might have an applied torque if I have an actuator at the base and I want to apply some torque so that I can move that pendulum around. But I might also have some friction in the joint. Okay, friction is going to come in, into the applied forces here. So for our purposes, those are the two of interest. I'll choose this to be some sort of a frictional term, or damping if you want to call it. Okay. plus my applied control input. Let's say I'll call it U here for consistency with what I've written before here. And you should see this as just a very simple scalar, but it's just a version. I could have written this in my more general form that we used last time, right? I could have written this as it certainly fits. I get theta double dot over here. It turns out that m is just, it's not even a function of theta in this particular case, right? You know, this fits into here, this one fits into here. It all snaps into place. Okay, so this is just the stuff of differential equations. This is like, you know, 1803. If you've taken that, right? This is it's a standard ordinary differential equation. Ordinary differential equation. So the standard question that you would solve with the tools of 1803, for instance, is if I were to give you the initial conditions, here I'm going to, since it's a second order equation, I'm going to have to give you two initial conditions, right? I'm going to give you theta at time 0, theta dot at time 0. Then you should be able to tell me theta is a function of time, right? That's the standard. Everybody remember how to do that? Turns out you can't do that in closed form for these equations, right? So most of the stuff in 1803 is actually for linear differential equations. And when you have nonlinear differential equations, you can integrate theta dot as a function of t just fine. But theta as a function of t is actually, it's an elliptic integral of the first kind in the very best case when b is 0 and u is 0. It gets worse than that when, you know, but it doesn't have a closed form expression in the general case. Okay, because of this annoying sine theta. If that sine theta wasn't there, we'd be gangbusters. But because of it, things got really hard really fast. So that's a little frustrating because the whole class is supposed to be about, you know, rigid body systems with pendulum-like elements, and if we can't even solve one pendulum, then, you know, where are we? And the answer is that actually, you know, there's a lot of things you can do without having to be able to analytically solve the differential equation. Okay, you just have to ask different questions. If you want to certify that your UAV is not going to run into a tree, or that, you know, it's provably safe, or it accomplishes a task, or something like this, you know, you probably won't be able to answer the question, where is it going to be at time 32 seconds, or something like that. That's a hard question to answer for most of these systems. You have to ask different questions. You can ask questions like, will the question of will it ever run into a tree is a question that we can actually answer without closed form solutions to the differential equation. Is it safe? Will it converge on a fixed point? You can answer those questions perfectly, not without, I mean, you can certainly numerically integrate these things. You can make numerical approximations, but you can actually make perfect statements about the long-term behavior of this system, about its not colliding into trees, without, you know, without numerics and without analytically solving that. Okay, so let's start that process today, and we'll do it, you know, I think more visually than, we won't bring out the big computational tools until the next lecture, okay? I'm actually going to try to channel Steve Strogatz, who's what I think a fantastic teacher. He teaches a great class on nonlinear dynamics. His book is excellent. I recommend it if it's not on your shelf. And he's got just a very graphical way to talk about a lot of these complicated systems, and we'll see if we can do that here today. We'll start with the pendulum. I'll do a couple other examples like some basic neural networks and recurrent nets and stuff like that. Okay. Yes, please. I can move the podium, sure. Can't tell you where it'll be at time t, but I can get it over there. Okay. So let's start getting, a complete understanding of the behavior of the pendulum without integrating the equations explicitly. And to start that, I want to use graphical analysis. Okay. And we're going to start it even simpler. So we're going to take the pendulum in a particular regime where I can draw everything in 1D, and then we'll do everything in 2D in a few minutes, okay? So how do we make this even simpler? There's an interesting regime where we've got so much friction that the pendulum basically acts, instead of like a second-order system, it acts like a first-order system, okay? But making sure we get that argument right is important to me, and I want to make sure it comes across to you, right? So we know that b theta dot is the damping term. And I want to say we're in a large damping regime. So what does that mean? Does that mean B is big? Sort of, but big relative to what? Right? What I really care about, to try to think about this as a simpler system, is that this term here, ml squared, theta double dot squared, plus b theta dot, in the equations, I want this term to dominate this term. I wanted, this term's contribution to be big enough that I can sort of ignore this one, and it disappears. So it's close to saying, it's tempting to say something like, maybe if b is a lot bigger than ml squared, that would make me happy. But that, for me, is like a parse error, right? My compiler just said, that's not allowed, right? Those are different units on the left and then the right, right? You can't compare two quantities if they're in completely different units. That doesn't make sense, right? So the units of ml squared, of course, is kilograms per meter squared. Anybody know the units of a damping coefficient? You don't? Sorry? Newton seconds per meter, that's true. I'll write it in kilograms, meters, squared per second, right? Same thing. I think that's the same thing. Newtons, meters, probably. So we're off by, so another way to see it, if you don't remember that off the top of your head, every term in this equation, I called it U. Let's stick with U. Every term in this equation has to have the same units. Otherwise, I wouldn't have been able to add them. They're all in units of torque, which were Newton meters. Okay. We know that theta dot has units 1 over seconds, right? Radians over seconds. Okay, so this is the bit that's missing. So in order to compare those two, I need to find some sort of relation. I need to change units. I need to have some sort of extra s that comes in. And it's a simple argument algebraically, but it's a sophisticated argument, I think, dynamically, in the sense that you want to think about, what am I actually trying to do? I'm saying that for most of the theta double dot pairs that I will see when I run this system, I would like to, get this quantity to be, this quantity to be almost always bigger than this for all of the sort of characteristic trajectories of the system. So so there's this notion of a characteristic time constant that could be your magical S that tells you, most of the time when the system's running, theta dot and theta double dot are related by this characteristic time constant. okay? It's an averaging kind of argument, okay? But for the simple pendulum, a characteristic time constant would be the natural frequency, or 1 over the natural frequency of the system. That gives me the natural frequency that we can write down here. Square root of g over L is the natural frequency of a pendulum like this, okay? Let's check our units. That should be meters per second squared over meters squared gives me 1 over seconds. That's what I wanted. Okay. So I actually want it on this side, but I'll write it on the other side. So what I want is to say something like that has the same units on both sides. That's a reasonable thing to say. There's a parameter regime of interest where my scaled damping is significantly greater than my inertia terms. And over most, over the sort of characteristic trajectories of the system, I expect this term to dominate this term. This is a very powerful skill. If you want to say something, about a single robot, about a single, like some of the best work I think that uses these, I see some of the very simple, the general results in walking robots often are written in this language where you can write the sort of canonical dimensionless variables of the legged robot and say something that's useful, or useful observation for kind of all legged robots, right? Which is much more powerful than said, I built this robot. It has mass this, it has inertia this, it had this property when I ran a simulation, right? If you can say a more general statement, then you've contributed more. So when we're in this regime, my claim is that this is bigger than this, and therefore I can effectively ignore this equation, and that my equations of motion simplify to b theta dot plus mgl sine theta equals u, or they're well approximated. So I'll do one more simplification. I like to write it just to be super clear that I'm not going to worry about the fact that theta wraps around every 2 pi right now. I'll just say bx dot plus mgl sine x equals u. I've done nothing but change the symbol, but it'll remind myself that I'm not worried about the wraparound effects just yet. So this this over-damping regime is interesting in many situations, right? So some of you have done fluid dynamics, right? This would be like the low Reynolds number regime, where the inertial effects are small and your viscous effects dominate. And you can, if you think about, I've thought about, flapping robots that are in honey, for instance. In the limit, where you're thinking about a flapping machine in a very viscous fluid, then you can make these first-order approximations, right? Maybe less common for pendula, but easier to draw. So let's do it. Okay, here's the trick, the first trick of graphical analysis. If this is just a first-order differential equation, right? Control differential equation. If I have this function, a function like this, even if f is very complicated, I've got a sign here that was too complicated to integrate, but it's not the worst you're going to see, okay? You can find out so much about it by drawing a few pictures. And the first picture you always want to just draw is just the function f here. So I'll draw it for u equals 0 first, but if I draw x versus x dot, it already tells me a ton. What does it look like for this? well, it's a sine wave, basically. It's a negative sine wave with its peaks at MGL over B. And it's negative sign, so it's going to look like this, right? Pretend that touched. Okay, now we can very quickly introduce a lot of the lingo from nonlinear dynamics on this picture. One of the first bits of lingo you want here is the notion of a fixed point. A fixed point x star, I'll even think about an autonomous system because I've set u to 0. So for x dot equals f of x, a fixed point x star is such that f of x star equals 0. Those show up nice and easily in my graphical picture here. I can just highlight all of the values of x there where x dot is 0. Right? A fixed point means, of course, that if my system starts in x star, it'll stay in x star for all time. So deterministic systems so far. Okay, but I can do a lot more very quickly. Okay. One of the great things about a one-dimensional system is that the flows of the system are potentially hard to integrate in time, but easy to talk about in the long term. Because for every state here, every possible x here, where the curve is above the line, I know that x is moving in this direction, right? And every place where it's below the line, I know that x is moving in the other direction. Okay? And I could just go through, make my pictures here. In Shebam, you basically know what's going to happen to the long-term behavior of the system. If I now ask you for this system, and I give you an x0, and I ask you where is it going to be at time infinity, you can tell me the answer, right? You can't tell me where it's going to be at time 32, but you can tell me where it's going to be at time infinity. And in particular, it highlights that there's a couple different types of fixed points in the world, okay? This one has the property that if I'm away from the fixed point, I converge back to the fixed point. We're going to call those stable fixed points. This is has the opposite property. If I deviate from that fixed point a little bit, I'm going to diverge. That's an unstable fixed point. So I'm going to color in, just by convention, I'm going to color in my stable fixed points. And in general, I want you to think about every crossing from above to below here is going to look like a stable fixed point. Now, there's a lot of different types of fixed points in nonlinear systems. We're going to go into it in just a second here, right? But you can imagine, so a linear system, if this is a linear equation, x dot equals ax, there's only so much that can do, right? It's only, I might as well go into it right now. Okay, so, you know, my plot, x versus x dot, you know, it gets more interesting in high dimensions, but still, it's got to go through the origin at some slope, right? It's going to have a fixed point at the origin. It could be stable or it could be unstable, depending on A, right? If A is negative, it'll be a stable fixed point. If A is positive, it's an unstable fixed point. That's all that my little linear system can do, okay? Well, it can be 0. We'd call that a marginally stable fixed point. But Nonlinear system has no such limits, right? Even in one dimension, things can get sort of fishy or more subtle, but certainly in higher dimensions, pretty much, like I said, it's a non-elephant, so anything can happen, really. You can have trajectories will diverge to infinity in finite time, or converge to zero in finite time. You can have all kinds of crazy stuff, okay? But you can imagine even in the picture here, you know, I can have multiple fixed points, for instance. I've already done that. I can have, you know, glancing blows. You know, I can touch and then move away. What is that? What do we think about that? Is that a stable, not stable, marginally stable? Okay, there's an answer for all of these. So let me give you the most important ones now, because they matter. They will actually change the way you need to code your algorithm later. Okay, so a fixed point x star. So I'm already going to say that it's touching that f of x star is 0. Is locally stable. Locally stable in the sense of Lyapunov. Which we'll typically write ISL. We'll give our first precise definition of what we could mean by stability. So in the sense of Lyapunov, we're going to say that for every epsilon, there exists a delta greater than 0. These are both meant to be small but positive numbers. There exists a delta such that if x0, if the distance in some norm, you can think of it as just the actual Euclidean distance for today, that's fine. The norm, you could write this in any norm, okay. That, let me write it out and then we'll talk it out. How many people have seen Lyapunov stability defined like that before? Okay. So if I have a fixed point of my pendulum here, let's say at the bottom, it's defined as, let's say, theta 0, theta dot 0. The game becomes, if I were to pick any small envelope around that, saying I'm allowed to be, you know, up to 2 units, you know, maybe it's, you know, so 2 units in my state space away. If you can, I want to say, I'll do it in higher dimensions first here, but let me say it. If I have x star here, I want to draw a ball, an epsilon ball here. I want to say that all trajectories are going to stay inside this ball for all time. Okay? That's this condition here. For all time, the trajectories will stay in there. I'll call it Lyapunov stable if, when I give you an epsilon of whatever size, you can give me a delta. It's going to be smaller than epsilon by definition, or by the derivation here, such that if the initial condition starts in here, even if it walks out or whatever, it'll stay inside epsilon as it goes. Okay, it's two circles. It basically says in the 1D picture, it's very simple. It basically says that if you stay, I mean, delta and epsilon are always going to be the same in the 1D picture. Okay, that if you start inside a region some distance from the fixed point, then you'll stay inside that region for all time. In the higher dimensions, delta can be different than epsilon. Okay, so this is not saying it will converge. It's just saying it won't go too far away. Yes?
It's not obvious to me that in one dimension, epsilon can't be bigger than delta.
You saw me pause and think about it, but I think that it has to be that way, right? So for a flow on the line, could take the case where for epsilon to be greater than delta, you would want to have a place where if I started inside, I could move away and come back. Of course, you can choose delta to be smaller, but you could always choose delta to be epsilon. You could choose a smaller delta, but you need not have to. Yeah. The maximum delta would be epsilon. Okay, so this is a relatively weak form of stability. Yeah.
I'm having trouble coming up with an example where you showed this like pink circle where you said the things can go out of the pink circle.
Yep.
I'm having trouble coming up with an example of a scenario where you couldn't draw a circle such that it wouldn't go out of that circle.
I'll give you one before the end of the lecture. Promise. And I think the teaser or the spoiler, I guess, is that there's no reason why it should contract in whatever norm you picked here, the Euclidean norm, right? So, for instance, if it takes trajectories of constant energy, right? That would basically put you in a ball that of constant energy. The radius of constant energy doesn't necessarily have to be a Euclidean ball. Okay, so you might stay inside a level set of some function, but not the ball in R2. Okay, so that's a weak definition of stability, but it's robust in the sense we can evaluate it. It's precise. We can evaluate it in lots of different settings. If we want something that's a little bit more like maybe what we thought of for stability, which is that we actually converge to the equilibrium, then there are stronger notions of stability. I'll say X star is asymptotically stable if it's stable ISL and x of 0 equals x star plus epsilon. If I started near the fixed point, it's always locally here I'm doing, that implies that the limit as t goes to infinity that I'll actually get there as time goes to infinity. This condition, this property here of converging as time goes to infinity to the origin does not by itself imply this property. You actually have to, asymptotically is defined when you have this and this. If you only have this, it's called you're attractivity, okay? And we will see examples of that, but that one's not quite as core in my mind. It's you can certainly construct examples like that. And finally, the other super important one, exponential stability. Says not only that I'm going to get there, but I'm going to get there at some rate, right? I started at x0 equals x star plus epsilon, then x of t, the distance between me and the fixed point, is going to be bounded from above by some exponential function of time, where c and alpha are positive constants. So that's just a stronger exponential stability does imply asymptotic stability. Okay? And it tells me some rate. Now, the solution to a linear differential equation is an exponential, right? I'll put it up here. If I have x dot is ax, then the solution to this one, linear differential equations I can integrate, are x0 e to the at. Let's finish this thought. Yeah. Okay. So in fact, a way to certify exponential stability, graphically if you like, is if I can find a line here, a linear system, for which this converges even faster, right? If this is locally, it's always above this line and below this line, then the performance of the convergence of the linear system gives me a certificate of exponential stability for that fixed point. Yes, please.
I was going to say, should that alpha be negative in exponential stability?
Oh.
Above?
Yeah, I forgot my negative sign. Thank you. Yeah. Yeah, I want it to go down, not up. That's important. Thank you. Okay, so this is like a super useful thing. It's good for robots. It's good for, I mean, I've used it recently in some work we were doing on trying to come up with convergence rate results in machine learning. And we were trying to show that an algorithm converged with some rate, right? There's the standard tools for machine learning for convergence rates are the same tools you see here, right? That you might have heard of, if you've thought about machine learning theory, you might have heard of like the PL inequality. It's basically trying to find these lines, right? There's some subtleties. There's one other trick in the PL inequality, but roughly you're trying to find the rate of convergence by bounding, the convergence by some exponential function like this. So I find myself coming back to these, when I need to think about something like this, I often try to construct a 1D example and see if I can start thinking about it graphically. It's super general. F could have been anything for me to draw these pictures, right? So a fun one I like is to think about some neural network models, recurrent neural network models. Let me tell you about the simplest version of a recurrent neural network. Okay, it's called an Autops. So just to set it up here. So if I think of my neural networks, this is, I'm going to just give you my notation. I'll call the input U, since we like dynamical systems. The output Y. Maybe I've got a tanh nonlinearity inside there. Call this W1, U2, U3. Okay. That would be a standard sort of feed-forward neural network model. But more interesting models of neurons think about the dynamics of the neuron, that actually real neurons take some time to build up activation, right? And then they're spiking models. But if we associate a state with this, thinking about it from its neural underpinnings, we can think about the state of this system inside here as corresponding to the average, a time average firing rate, or a moving average firing rate. We'll just call firing rate of the neuron, okay? And a simple version of this would be to say that maybe my firing rate depends on the inputs, something like tanh of the sum of W I U I. Time n. And of course, in recurrent networks, things get interesting because I can potentially take the output of my neurons and wrap them around back into my inputs. Okay, so maybe I even have some xn plus 1 is tanh of some of wx I plus some exogenous input. And actually, the simplest recurrent neural network that you can think about is a single neuron that's just in feedback with itself. Okay? And that's what an Autops, that's called an Autops. Okay, it turns out it's a real thing. It probably doesn't, well, we don't know really if it happens in the brain, or certainly I don't know, maybe people. But this is something that the professor I did my PhD with worked on. You can make these happen in a culture, okay? It's kind of cruel, but I guess, well, I don't know. You've already taken the cells out of the animal, so maybe it's not mean anymore, but still, you've got a culture of neurons in a dish, right? And you roughly let all of them die except for one, and then you put it in hibernation roughly, and you try to nurse it back to health, and it reaches out. You basically put these chemicals in to kill off all its processes, and then it tries to nurse itself back to health, and it reaches out and grows its dendritic processes, its axons out, and it's making connection with anybody it can, which is only itself. Okay, and you get these weird cell cultures that have, one neuron with its, connecting back to itself. Okay, and they have very interesting properties. Okay, like I said, we don't know if they're representative of the brain, but they certainly were representative of the way people started thinking about memory in the brain by saying that maybe a model of persistent short-term memory is actually by the stability properties of the firing rate of these neurons that are in feedback loops. So we're going to be able to take those stability concepts, plot them for a simple model of a neuron, and see if we can get something that looks like memory to come out. Kind of cool. I've been using the language of continuous time systems. And this is what I've written here is discrete time. The continuous time version of it is if I just take this and say that this is approximately xn plus, let's say, dt x dot of n would be sort of my Euler update. Okay, I'm going to just, you can call this a time constant, and what you end up with is a tau x dot plus x equals tanh. And in the Autops case, I'm not even going to worry about exogenous inputs. And I've only got one of me, so it's the simplest scalar version of that equation, which is this picture with a connection back to itself. I'll even set tau to 1 for now, just one less parameter to mess around with. Okay? So let's plot that function. I solve for x dot. I've got two terms. I've got a minus x, which is kind of like this. It's exactly like that, I guess. And then I've got a tanh function, which I think people know, but maybe a couple of the properties we should be careful about here. So tanh goes from -1 to 1. It crosses at the origin. And in particular, it crosses at the slope 1. Okay. So tanh of wx is approximately equal to wx when for wx approximately equal to 0. So it crosses with slope 1 there. Okay, so if I want to plot this over here, I'm going to have minus x plus tanh of x, so it's going to modify my minus x. And it's going to go something like this. If w is 1, then it's going to just have this grazing intersection with that line, okay, and go down. Cool. So where are the fixed points of the system? Yeah.
Could you turn the overhead lights on?
I was thinking that, but let me try that. Hey, hey.
Thank you.
Sure. So where are the fixed points of this system here? I can maybe use allocate one of my colors to that line here. Well, I've got a fixed point here at the origin. Is it stable or is it unstable? Stable. Okay. It gets more subtle if I asked you which type of stability it is. Okay. Good, because but now let's make W 10, right? Something bigger. So this was W is 1. Let's do W's 10. Now that's going to increase the slope here. It's going to put me something more like this. Okay. Now there's 3 fixed points. Stable, unstable, stable, right? This is, let's call it 10. Okay, so now this is an interesting phenomenon that people, talk about often. It's useful in electronics, it's useful in models of memory, right? This is a phenomenon of bistability, right? There's 2 fixed points, and you can imagine moving the system into one of these fixed points and sort of latching. You can think of the system as sort of latching in a memory, and I'll try to make that more clear in just a second. So what if I were to now say I had an additional input? So if I have x dot equals -x plus tanh of wx plus u, some exogenous input. If we think about what this is doing to the tanh, if I just, it would kind of shift the tanh back and forth. It's like moving my x, right? So in this picture, if I were to add a u, it would shift me this way or this way. In this picture, it's shifting me that way and that way, right? So I could get pictures like this. or down here. Okay? So with a little bit of U activation, if I push that neuron a little bit, I can actually change, even remove the fixed points of the system. Okay? So for instance, if I apply some U, if I want to latch in this fixed point, for instance, if I could send a pulse of activation, you know, if I were to say, I'm going to stimulate the neuron for some amount of time, just send a pulse, right? And lift the curve up here, let the dynamics settle, flow over to here, okay? And then bring it back down to 0, it's going to stay in that fixed point. Persistent memory based on the feedback connection at the neuron level. If I even wanted to push it back the other way, I could do that. You know, kick me back the other direction. So that's pretty cool. That's like a simple model of memory. Now, of course, the neural networks in our brains or the neural networks in our PyTorch code have a lot more than one neuron, and a lot more is possible. But there's some neural models that very explicitly talk about this latching memory, and some of them just hope that something cool comes out of gradient descent, you know. But it was certainly the heart of a lot of the early models of you know, neural memory, models of memory. And you can see it all on a graphical analysis. There's a variant on it, a very popular variant. You know, the ones that people, so not many people use Tanch. You know, there's certainly the Autops model in PyTorch, right? LSTM. How many people know LSTM? Long, short-term memory is a popular model, neural model for to actually be used in a recurrent network in machine learning. It's got the same building blocks, people, and it's slightly different letters. Sorry, I didn't remake the figure with the same notation. It's got some tanches hiding in there. It's got some sigmoids, which are a lot like tanch, but go from 0 to 1. You know, a bunch of things lopped together. Okay, it's built from the same parts. Okay, but it's got a couple different connotations. One of the motivations behind sort of using this as the key unit of a recurrent neural network is the idea that if you're trying to simulate neurons for a long time, their gradients can get very bad. You have this vanishing gradient problem. Okay, we'll talk about gradients a lot later, but if that means something, that's useful. The LSTM has these extra inputs and extra activations which are trying to explicitly latch in or forget the activation of the network. Okay, and we can see that. I'll make a version of this that's simpler than the full LSTM, but that we can see you know, directly in these pictures. A simpler model, there's a JNET model, which stands for just another network, which is a simplified LSTM model, which basically just has the primary activation, the tanch, plus a forget gate. So it's like maybe they think that's the key aspect of LSTMs, and they captured it only, and they did a bunch of experiments to say that was the most important element of LSTMs. Okay, so the model looks like this. I've got an extra forget, we'll call it F of n here. Where f of n is just another input. This is my sigmoid activation. It's very similar to tanch. if you do the continuous time derivation, you get the x plus x equals that stuff. And instead of just drawing it all, let me try to animate it all for you here. This is in the notebooks, for the chapter here. So first of all, I'll do the original Autops. I swear that it's the Webgl doesn't draw lines well on Mac. So that if you're looking at that, you're like, why didn't he make the line a little thicker? I tried to make the line a little thicker, but it's not it was past my pay grade. Like at some point, if Webgl doesn't respect the line width property, then I'm not going to fix it. Okay, so, but otherwise, this is the original Autops, and I put little sliders in the GUI here. This is W, and this is U. Okay, so first let's confirm what we already said, that if we make W bigger, we can get our curve to go up like this. And if W is less than 1, it goes down like this. And we have those fixed points, okay? And then U, if I move U like this, I can have that positive fixed point. If I make U negative, I can have a negative fixed point. Okay, hopefully this will be useful. I hope it's useful to play around with. Let's see what happens with the JNET model with this extra forget gate on top of it. Same plot, okay? And in fact, when W and U are 0, then I get exactly the same behavior. When I'm not trying to forget anything, I have my F is 0, so I just get the original equations back. I get my same tanh behavior. Okay? X just like I did before. But now, if I were to go in and say forget, then I can set it down. So I added a little bit of decay factor here, but basically if I turned on the forgetting, what does it do? It wipes my memory, sets the dynamical system to have a new fixed point at the origin, and I've forgotten, right? Now you can then, of course, stop forgetting, and you're receptive for new inputs once again. If you change and start adding this extra, start changing the gains of the forget, then you get something that those of you that play a lot in PyTorch will probably recognize. If I can probably make this look a certain way. It's basically the Swift or the CLU activation, because it's basically a sigmoid times the x. It's an activation people like. Somehow it learns well. Maybe it's one of the mysteries for why LSTMs work so well, is they picked the right activation functions. Okay, but I only have a plausible explanation for the forgetting when W is like that, and that looks like a nice, changed my dynamical system back to wipe my memory. Does that make sense? So in your homework, so people have taken this idea, and before we had big GPUs and PyTorch, people were using this to build models of memory, even before we trusted that, let's say, gradient descent could find these things. There's a version of this proposed by Hopfield, saying that recurrent neural networks can store memories by just choosing the weight vectors. He gave a recipe that doesn't require gradient descent, just an explicit way to set the parameters of W, which for a simple network model has exactly this idea of latching memories blown up so it can store some finite number of memories, even in images. And we'll be able to let you play with a version of that in the PSET, okay? And the picture he has in his head is now it's higher dimensional. You're moving in not just one dimension, but you can basically program the fixed points of a simple recurrent network by choosing the weights correctly. And then memory is if you put an image in that's similar, that's as close as possible, let's say, to the image of the dog, it will actually, the dynamics of the network will converge to the picture that you stored, just by the activations being stored in the, by the memory being stored in the weight, so that the activations have a fixed point at the memory. Yes?
This might be a dumb question, but I like the fixed points that hold or retain the information. Like, where is like the actual remembering happening?
No, that's a great question. So this is why there's this distinction between short-term and long-term memory. Okay, short-term memory, people are saying that in some sense the current activation is kind of like what's happening in your head right now. That's what your neurons are firing right now. But that's going to your neurons are going to get tired. That's going to turn off or whatever. The way you store a long-term memory is by changing the weights of your network. I mean, the LSTM long-term is also about latching. But when people talk about a memory that persists for days or whatever, that's like you've changed the weights of your network.
So like in that like specific region, let's say maybe in the equation we're trying to keep xn plus 1 and x at n like as close as possible, maybe?
X is only relevant for the short term. Okay, so let's say when you're learning, when you're seeing the dog for the first time, you're going to have neurons turn on that, for instance, are some feature vector of the dog, are my activations. Okay, and then what you'd like to do is that the next time you see like half a dog because it's behind the chair, you'd like that the weights have changed in such a way that when I see half the dog, the rest of my neurons that remember the full dog turn on. So the initial conditions X converge to the full memory of the dog. That's dramatically oversimplified, but that's the basic idea here. Sure. Yeah.
Would the get function in the JNET model then also be changing the weights?
Say it again.
The JNET model you have there, how
Yeah.
does that then work with that changing the weight that it goes, right? Because the get function, if I'm understanding correctly, slowly decays the activation. But then you guys are going to change the weights as well, yeah?
Correct. So there's a second step required to actually change the weights. These days we would do it by doing gradient descent over the trajectory, for instance. This particular was a shortcut where it's a simpler neuron model, but they know what the solution to gradient descent should have been. They could just say, set your weights like this, and it will have the right fixed points. Yeah, sure. That's great. Okay, so that's a pretty powerful set of tools. There's one more sort of definition or set of definitions that I want to give you with this. Okay, so we talked a lot about fixed points and the basic stability and instability. We can also talk about, and the picture there sort of suggests it already. If I want to talk about this fixed point, I can talk about the basin of attraction or the region of attraction of that fixed point. So okay, so if I can figure out what are all of the initial conditions X, which once I start the dynamical system will converge on this fixed point, that defines a region in this space, which of course in this space is just on the line, defines this region, which is the region of attraction of that fixed point. So if we want to go beyond our local statements of stability to some regional statements of stability, then we start talking about using the language of regions of attraction. And that's exactly what Hopfield or Hertzkrow and Palmer drew in the thinking about the Hopfield network, was these regions of attraction converging to different fixed points. And in fact, these boundaries also have a name. Those are called the separatrix. They're the boundaries of the regions of attraction. And because these fixed points and regions of attraction and everything can change over time, let's say during learning or during, it's a function of my parameters here. There's another important notion I'll introduce here. Which is the notion of a bifurcation, in particular the way you draw a bifurcation diagram, okay? So let's think about the Autops model here. We'll say u equals 0 for this case. And what I'd like to plot in a bifurcation diagram is the sensitivity of the fixed points as a function of the parameter w. And this is in the spirit of just, all of the wonders of nonlinear dynamical systems, okay? We drew it already a little bit here, but for the Autops model, my simple tanh, we said when w was less than 1, I had a single fixed point at the origin. So for w less than 1, I have a fixed point at x star equals 0 up until w equals 1. After w is 1, right, this is my, turn this back to 0, up to 1, so this for less than 1, I have a fixed point only at 0, and it's stable, it happens, okay? And then when I get to greater than 1, I still have a fixed point at the origin, but it's unstable. And I sprout 2 new fixed points, which actually have a beautiful behavior. They also asymptote to 1 and negative 1 here. Except for maybe a toy one. I think we didn't even include this one in the piece. Or did we include this in the piece set? Yeah. This isn't necessarily the most important skill for you to have, but it tells you about the wonders of what's happening in these neural models, right? Or in nonlinear dynamics in general. Fixed points, as you change parameters, if I'm changing my weights of my network during learning or whatever, I can actually have the behavior change in a very punctuated they're called bifurcations, this point where the number of fixed points even changed, okay? The stability of the fixed point changed in a categorical way, boom, right? And I've sprouted new fixed points. And even in very low dimensional systems, there's all kinds of interesting bifurcations. This one's called a pitchfork bifurcation, go figure. There's all kinds of funny names for bifurcations that happen. And I can only imagine what's happening in like 1,000 ReLU or 1,000 LSTM network that's being trained on some sequence modeling task. Just even think about what could be possibly happening inside there. Who knows? Okay, but there's just beautiful, beautiful insights from dynamical systems that at least get us started and ground us in the simple cases. Okay, people feeling like they're getting a gist for nonlinear dynamics? I have to take you back to the full pendulum, otherwise it's, if I say that we're going to just understand the pendulum and we don't even get to the second order pendulum, that's kind of a letdown. So let's do that. All right, so let's do the full pendulum now. ML squared theta double dot plus B theta dot plus MGL sine theta equals U. Now I've got 2 variables coming around, right? So if I want to write this as x dot equals f of x u, then the way I would do that would be, I'm going to say theta and theta dot is my state space. My dynamics, I would write as theta dot, and then use this equation for the derivative of this, right? So this is theta double dot, which equals, 1 over ml squared u minus b theta dot minus mgl sine theta. So I can't draw my beautiful, x dot as a function of x. I've got 2 x's and 2 x dots. I have to start drawing, trajectories in state space. And I think many of you will think naturally in this way, but it's, at least in the case where we have only 2 variables, you could still do a lot of things graphically that are complete. There's not anything hidden in the dimensions you haven't plotted, okay? So if I were to plot now an evolution of the system in x versus x dot, so let's say I had some trace of the system, then the derivative at any point is x dot here, which is my dynamics, which is this theta dot versus theta double dot. This is called a phase portrait for the dynamical system. And the phase portrait for the pendulum is going to be super important. I want you to make sure you recognize it and feel comfortable with it. We're going to use it for control. We're going to use it for analysis. It's like a great fallback. Okay. So I can plot curves through this space by simulating the system and plotting the whole line, or I can kind of try to draw the whole thing. I could just draw these x dots as little vectors at lots of different places, and then realize that if I were to simulate, it would be connecting the vectors. Okay, but really what I have is a vector field floating around here of all these different vectors. Okay. And for the case where u equals 0, let's even do b equals 0 and u equals 0 here, I could take this equation and I can say that I can just draw the vector field. Okay. Each vector has 2 components, right? Theta dot and theta double dot. So if I want to draw the cases where theta equals 0 and theta dot is not equal to 0, then I could start drawing those as, I've got 0 here. The y component of that is always going to be 0. Did I say that right? The x component, sorry, what have I done? What have I said wrong here? If theta equals 0, this term equals 0, so this term could be not 0, and this term is b. Oh, but b, I said b to 0, that's why. Okay, sorry, b is 0, so that term is 0. Yes, that's why. Checking my assumptions myself there. Yeah, in the b equals 0 case, it's just like this. The other thing that we can plot here is when theta is non-zero and theta dot is 0, then the x component is 0, and I get my sine wave here. And similarly back here. And if I were to plot it in here and figure it out, I'd see stuff like this. Okay, and there's this, very quickly, we can see a lot of super important things about the pendulum graphically. So first of all, We still have a fixed point at the origin, even in the full pendulum dynamics. We have a fixed point here and here in every 2 pi. Every pi. That corresponds to the upright fixed point, yeah, and the downright fixed point. When there's no damping, when b equals 0 and u equals 0, then we have these, if we were to simulate from here, we'd actually get these closed contours like this. And it elongates in a way that goes like this. Oops, into my fixed point. Okay. And then up here, it does something different. It goes around like this, because this one's got another set of closed contours like this. And in fact, if I were to do the same plot in the case where I have damping, then damping only changes my y component of my vector field. And it tends to shift it towards the origin. So the damped response is going to go like this. And the orbits, you won't be surprised, spiral in like this. Okay. Out here, it's more interesting. It can go around, and then depending on how much damping there is and how much velocity you started with, you might get caught in here. You might go over here. Sorry, not like that, like this, and get caught in. You can't go this way on the bottom. That's like, all right? But there's all kinds of beautiful things possible. Is this fixed point stable? This one at the bottom. You should say, that depends which definition of stability, because now it matters, right? Okay, so is this fixed point stable in the sense of Lyapunov? Okay, for both the blue undamped and the red damped, we have the property that if we stay close, you pick a circle, I can pick another circle inside, right? This answers your question, right? Is that these are contours of energy, not circles. So you might have to make your inside circle smaller so that your contour of energy fits inside that, right? But in both cases, the red and the blue are stable in the sense of Lyapunov. Only one of the two, though, I mean, only the red is stable in the asymptotically, right? And these differences will compound in more and more complicated systems. Okay, so I'm going to end here with just an idea, I guess, quickly. So let's think about how U enters here. It also only affects accelerations. So just like damping, what U, the controller, and U, the letter, gets to do is you get to move the vector fields up and down. If you're going to write a controller, you can choose, you can sort of individually address the different vectors, if you will, right? You're allowed to write a function over the space which moves them different amounts up and down at different parts of the space. So your job, the way I want you to think about control, is that nature gives you a vector field, right? You get to tweak it. We could, if you're doing the feedback linearization thing, you could erase it and draw your new vector field in, but don't do that. That gets some jobs done, but it's not going to get you ultimately where we want to be. Okay, high efficiency, super efficient, super high performance robots. All right. So the way I want you to think about control is, nature gives you a vector field. What's the minimum amount you can do? You get to just pull a couple strings, do a little bit of minimum change to the original vector field. so that the flows follow your command, move the fixed points as you want them to be, stabilize the fixed points that you want, destabilize the ones you don't want. Okay, that's the beautiful way to think about control, I think. You can see it in 2D, but it's the same thing for a humanoid. So we'll start doing control next time. Thank you.